Today we'll discuss about Gauss law. This Gauss law is concerned with calculation of flux through some closed surface. So let's begin with an example of calculation of flux. We'll begin with the simplest example. This is the example where we have a spherical surface of radius r and charge q placed at its center. We'll now try to calculate flux through this spherical surface. So let's begin. The very first thing is we'll have to take a small surface ds on this spherical part. So let's take that small surface ds. There's the small ds on the surface of sphere. Now we have to calculate flux through this ds. So we'll first mark normal to this surface. This is the normal to surface along the radius. Next, the field at this point on the surface. The field will be pointing along the radial direction. It points away from the charge, so this direction will be same. This is the direction of field. Now the field E, its strength at every point on the surface will remain same, and the strength of this field is kq by r square. So let's write the field. This is the field. Now proceed for calculation of flux through this ds. We know the formula for flux. E ds cos theta. Theta, the angle between electric field and normal. This is 0 over here. Both are in the same direction. So flux through the surface ds is eds, and cos theta becomes cos 0, which is 1. Put the value of this E from equation 1. Write it down this way. For net flux through this surface, we'll have to integrate this d phi. So net flux phi is integral d phi, this way. Put the value of phi from this above equation. This is the expression. We have just substituted the value of d phi from this equation over here. Now in this expression, this term 1 by 4 pi epsilon q by r square, this is constant. As this is constant, this can be brought out of this integral sign. So our equation will reduce and would take this form. This constant term brought out of the integral sign. Now this integral ds is this part. Now there are various such ds on different parts of the sphere. If you add all such ds, this will give you the complete sphere. So integral ds means sum of all such elementary ds. That gives you complete area of the sphere, 4 pi r square. Or for this integral ds, we can substitute 4 pi r square. So let's do that. And this is the result. Cancel out the expression, simplify it. This is the result. So remember this result. If we have a spherical surface with charge q at its center, the flux comes out to be q by epsilon naught. This is the result which we derived. Next, let's consider another example. This time we will not take a spherical surface. The surface would be somewhat arbitrary, and there will be charge q inside it. This way. This is the second surface. This is an arbitrary surface. But this time calculation of flux is not that easy. Every point on the surface, they'll have different value of E. They are not equidistant from the charge. So here, if we write down flux as integral E ds cos theta, E will be variable, theta will be variable. It's very difficult to get that way. Let's proceed with some other way. Let's again draw a sphere inside this arbitrary surface as this one, the previous one. Now we know the flux through this surface. It was q by epsilon naught. We just now calculated it. Anyhow, the lines which are crossing, the electric lines of forces which are crossing the surface 1 also cross the surface 2. So number of lines crossing surface 2, the second surface, is same as the number of lines crossing surface 1, because there is no source or sink of electric lines of force in between. They are neither terminated in the space between the two, nor they originate from here. So we can say flux through surface 2 means number of lines passing surface 2 is same as flux through 1, or number of lines passing through 1. This one is known. It's q by epsilon naught. So this is the result. Flux through surface 2 is q by epsilon naught. If I remove the surface, we are not concerned with the surface now. Its purpose is over. So we can say that if we have a surface, arbitrary surface with charge q inside it, the flux through it is q by epsilon naught. There is the result. The net outward flux through an arbitrary shaped surface depends only on the charge enclosed within it, and it is always given by this way. Phi closed is q inside by epsilon naught. Or for the we can express this in integral form as this way, or you could even write this E dot n cap as E cos theta ds, this way. Now if rather than having a single point charge we have 2 or 3 point charges, then also we'll have the same expression, but here q we'll have to take the sum of all charges, q1 plus q2 plus q3. Let's see this. Now here we have the same surface and there are a large number of charges inside it, q1, q2, q3 and so on. So without going into details, we can conclude that the net flux through this surface will be q1 plus q2 plus q3 plus q4 plus q5 by epsilon. All the sum of all the charges inside divided by epsilon. And this is what we call Gauss law. So Gauss law states that if we have an arbitrary shaped charge surface, the net flux through that surface will always be equal to 1 by epsilon naught times the charge inside it. The charges which are outside that surface, they would not have any. Suppose the charge is over here, this will have no contribution, this will have no contribution. So this is our Gauss law. The net outward flux through any arbitrary closed surface is 1 by epsilon naught times the net charge enclosed within it. And this is the expression. This basic formula is called Gauss law. Thank you.